Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth. Hello, folks. Today we are joined by Doctors Richard Vaia, Jesse Tice, and Anna Balazs to discuss all things nanomaterials, including what they are, why we need them, and how Scotch tape played a key role in getting this research to stick.
In 3, 2, 1.
Hey folks, Kenneth McNulty here with AFRL. Welcome to a unique episode of Lab Life. I say unique because, one, we have a number of awesome guests we'll get to in a moment. You probably heard at the intro who they are, but once they start talking, trust me, it's going to be even more exciting. But I have a unique co-host this time, who I'll stop speaking for. Please introduce yourself and give us a feel for why you're here.
Thanks, Ken. This is Branden Brough. I'm the director of the National Nanotechnology Coordination Office. And I'm super excited to be partnering here with Lab Life and with our friends at AFRL because we're going to be talking about nanotechnology today. And nanotechnology is the study of the incredibly small, sometimes at the level of atoms and molecules. And when you're working at that size scale, you have to have a team. You have to work with other people. You have to have a diverse set of experiences and perspectives. And that's exactly what we're going to be doing today. We are working with AFRL, with their Lab Life podcasts, and joining the power of the stories of the NNI, the National Nanotechnology Initiative, which is the United States' effort in all things nanotechnology. So I'm super excited to be part of your team, Ken, and to be part of this great group of experts here to talk about nanotechnology.
Right back at you, my friend. And honestly, I couldn't put it better myself. So I will say we're going to go ahead and start with something that one of my team leads love to say. You guys know Michelle, my team or co-host here. She likes to go big to small, which is exactly what we're going to be doing today. Let's get a big picture idea of who we're talking to and then get to the nano. So starting off, we're going to go with one of our own, Dr. Richard Vaia. So if you give a chance to introduce yourself, kind of what you do here at AFRL, and how you became involved with nanomaterials.
Yeah, Ken, thanks. Welcome, everybody. As Ken said, my name's Rich Vaia. I'm the chief scientist of the Materials and Manufacturing Directorate. What that means is, I guess, I'm the head geek for Air Force materials and manufacturing. My interests in this area, my interest in materials goes way back to when I was in high school. I enjoyed physics, I enjoyed chemistry, and I was one of, I think, the few people who, when I went to the Natural History Museum, I spent all the time in the gems and mineral area. I just thought they were fascinating. Ended up going to school to do materials, and as with many things, just was fortunate to land, I was in graduate school in an area that was emerging, which was nanotechnology. The experiments we did showed results that were unexpected. And all of a sudden, things took off. And after I separated from the military, I ended up joining the lab and have been part of research in materials, manufacturing, and nanomaterials and aerospace for about the last 35 years.
Now for our next speaker, I'll let him introduce himself and tell us all about what he does and what he's doing here and how he got into nanomaterials.
Yeah, thanks, Ken, for having me here today. I really appreciate it. So, I'm Jesse Tice. I graduated from Arizona State University, the School of Molecular Sciences, with a PhD in inorganic chemistry. I've been working at Northrop Grumman in Manhattan Beach, California for the past 15 years. I'm currently a consulting research scientist where I've built and managed a nanomaterials lab for the last 8 years. I was drawn to nanotechnology originally because it really combined the use of subjects that challenged me the most: chemistry, physics, and material science. And nanotechnology is at the intersection of that Venn diagram. So the challenging aspect really hooked me. When I went into grad school, I was making new materials for solar cells that absorbed a larger part of the solar spectrum, that increased efficiency, because I knew we needed more clean energy for the planet. And so that time that I spent learning more about chemistry, physics, and material science really helped me in the future, and especially got me hooked onto nanomaterials and nanotechnology. And in my current role, I actually get to work on incorporating nanotechnology into a wide range of our products, especially what I studied on in graduate school, such as solar cells and solar arrays. I was hired straight out of college. I worked in the chemistry labs at first, I was able to get out into the field and get exposure to a lot of the interesting air and space vehicles that we build, and use my knowledge to enhance our products and solve major challenges. I always gravitated more towards something that I could see, touch, and feel at the end of the day and know that my impact is out there. And I really enjoy, as part of leading the nanomaterials research lab, taking the latest advances in academia and literature and being able to apply those into our aerospace vehicles. And that's what I'm passionate about at the end of the day, and what makes me tick.
Dr. Balazs, please, the floor is yours to talk about who you are, what you do, and what got you into nanomaterials.
Hi, I'm Anna Balazs. I'm a professor at the University of Pittsburgh in the chemical engineering department, and I do computational modeling. So I try to develop new models that incorporate nanoscale to the macro scale. And unlike these other people, what got me into it was tree trunks. Because I looked at the structure of trees, when you cut them across, and you kept wondering, okay, that's a big thing. Then what happens if it gets smaller? What gets smaller? What happens if it gets smaller? So the interconnection between this macroscopic object and then what it's made out of is what really got me excited into science and also into nanomaterials.
Before we get into the beauty of all the wonder that happens atom by atom or molecule by molecule, maybe we take a step back. When we talk about nanotechnology, when we talk about nanomaterials, what exactly are we talking about? Maybe I can go to the head geek here to start us off.
Thanks, Brandon. I appreciate that. So I think we mentioned a little bit when we began, what is nano? You had mentioned it's the study of small stuff. One of the things I've always been fascinated with is just how small that is. A nanometer is 10,000 times smaller than a human hair. It was only because of inventions in the 1970s and 1980s, tools that even allowed us to start seeing things at that length scale in a reproducible manner. And I think that's what started the interest and explosion in nanotechnology. But in my opinion, it's more than just the scale that makes this area interesting. It's how that scale interacts with the physics, with how properties evolve, how atoms talk to each other, how the outside world interacts with materials. They all converge on that scale, anywhere from 1 to 100 nanometers. And why that's important is because when they converge, new things happen. When you put water in the ocean or on a pond, it can be flat. But when you put it in a bucket and I shake it, I create waves on the water. That's a result of the bucket that I put the water in. And that's what happens on the nanoscale. Whether it's mechanical properties, make things super strong, optical properties, make gold appear to be beautiful colors, or electrical properties that make atoms and electrons move in ways that is not possible in other materials or other structures. So it's all that together that makes nano so exciting, not just the scale, but what the scale does to the properties. And then the technology is, doing something with that.
One thing that Dr. Tice, you mentioned, you're talking about you're drawn to things that you could see, touch, and feel. And what I just learned from Dr. Vaia is all of these nanomaterials are incredibly small. So how do we see, touch, and feel things that are atoms or molecules?
Brandon, that's a great question. We've really had to develop techniques to do this over the years because, as you mentioned, we're working at the atomic scale. So how do we create something that you can visualize at the atomic scale? We've had to develop, as a scientific community, devices such as electron and atomic microscopes in order to be able to see at the nanoscale. And there's been great strides that have been made in those topics over the years, which enable folks like me to study the properties that occur at that scale. One thing that's really important for my industry is being able to pack a lot of multifunctionality into a small space. And with nanomaterials, we can do that. And one thing that's interesting that I'd like to highlight is recently we've done some work on a very unique tool that was developed specifically for nanotechnology. We've partnered with Brookhaven National Labs in New York. They have a device that they built called a quantum press. And what that does is it's able to exfoliate single atomic layers of what we call two-dimensional materials. And an example of a two-dimensional material is graphene, which became famous in 2010 for winning its Nobel Prize. But since then, a lot of two-dimensional types of materials beyond graphene have been discovered. And with this quantum press, we're able to build a library essentially layer by layer and study these multifunctional properties, including how they conduct heat, how they conduct electricity, and make devices where we can study their electronic and photonic behavior, it's just really neat to be able to control matter and be able to visualize it at the nanoscale.
So can just anybody use this quantum press? Where can you buy one at Target? Where do you get a quantum press?
You cannot, unfortunately. However, you can submit a proposal to use this instrument that is specially developed and only exists at Brookhaven National Labs. But you're able to, in the public, write a proposal, and if it's accepted, you're allowed to go in and work with the researchers to perform your experiments and study on this tool, which is just incredible in and of itself.
Well, I'll have to get my proposal writing going then.
So Jesse, I think maybe some folks can get into this area by buying Scotch tape, though.
That's right.
I mean, one of the things that launched the whole graphene area was simplicity and innovation combined. In your pencils, you have graphite lead that's made of these carbon layers. And folks were trying to get the layers apart. And one of the great innovations was, let's just take some Scotch tape and keep putting the graphite between, pilling it apart, putting what was there between two more pieces of Scotch tape and pilling it apart. And that was actually the first approach to get to single layer, atomic layer carbon. So if someone has a lot of patience, they can even do it in their home. But the Brookhaven allows you to do incredible architectures. It's an engineering tool now.
But isn't that fascinating to be able to take Scotch tape and just manipulate the matter to reduce it to an atomic scale and be able to study what happens as you reach that atomic scale? And as you mentioned, something as simple as Scotch tape really had a dramatic impact on nanomaterials and nanoscience.
So Dr. Balazs, you talked about using computational modeling. Now I'm guessing that those models are not the models that I used in high school chemistry with a bunch of wooden balls and sticks. And I'm guessing also you're not using a lot of tape to put together your models. So tell us, what is computational modeling?
Handy, you know?
What is computational modeling, and how might that be added to the picture of studying nanomaterials?
Sure. So before I answer that, I just want to reinforce something that Rich said, which is no material is created in vacuum. You know, it has to nucleate from something. And it nucleates from interactions between atoms and then those creating a strut or framework for larger species, and that makes a scaffold for even larger species. So it's that, again, aesthetic appeal of the beauty of trying to probe to the smallest dimension, but I'll say it, in all materials, in all natural materials, it does have to nucleate with something. So, and that's usually on the nanoscale. Now, the computational models that we use are ones that we developed. They're not available. They're research tools. And the fun thing was, I mean, we keep emphasizing this, is that to cross length scales. So if I would like to know when I mix the nanoparticles into a polymer, okay, so where are the nanoparticles? And so I have to bridge the length scale between nano and the critical characteristic size of a polymeric domain. So at the end of the day, so I know where they are. And then given that structure that I've gotten, what are its optical properties? What are its electrical properties. So I want to take after it's all assembled, I want to take a photograph, and then I want to feed that photograph into another program that reads it, and then tells me what are the macroscopic properties. So that's the kind of things that we've been doing.
So what are some of the fundamental questions you're asking that are really trying to understand what a nanomaterial can do? We've heard a lot about these new properties on the nanoscale. What are some of the questions that you're most interested in answering?
Well, let me take a historic perspective of what got me into this. There was this gorgeous paper that I came across. I know one of the authors, but Andy Levenger was one of the authors. I don't remember the other co-author. And it was looking at mixtures of nanoparticles and polymers and how they influence each other as they move around and evolve. And so that's what really grabbed me into this field. And then I can't remember if that paper included diblock copolymers or not, but there's this other interesting question. If you have things that are assembling at different length scales, so diblock copolymers form these beautiful mesoscale structures, and now if you throw in nanoparticles and they form clusters on nano to microscale, and they're both evolving, then how do they evolve together? And how can you drive that evolution to make a product that you would like to use? For example, we threw in some nanorods into a phase separating polymer, and we got the nanorods to form an extensive network to percolate across that domain, which means that you had electrical conductivity throughout that domain. And because it was in this soup of phase separating polymers, you didn't need a lot of nanorods or nanotubes. So it was this dance, and the dance continues, that one tries to probe computationally.
Yeah, if I could add, so Anna's description of the power of what she's done, the power of modeling, it does two things. One, it helps us understand what leads to the properties we observe as an experimentalist. You can't do one without the other. But I think the other power of work such as Anna's is the inspiration. The ability to do the modeling with the right physics tells you what can be done and what can't be done. And back to our Scotch tape comments, just imagine trying to build something one layer at a time, atomic layer at a time, with Scotch tape. I mean, that's not a manufacturable approach at all. But the dance Anna is talking about and the inspiration of some of her work showed the rest of the community that there's other ways to assemble things on the nano scale than picking stuff up and sticking it together like we do on the macro scale. You can use the interactions of the materials, and with the right temperatures and the right tickling from the outside, you can have the structure self-assemble or evolve. And that is key to the manufacturing at the nanoscale, is being able to harvest those types of interactions between materials, not only to give you the properties, but to assemble and create the architectures that you want. And Anna's work and other modelers not only describe the physics, but are a real inspiration to what can be done. I know I've always admired her work along those lines. She constantly comes out with, hey, why don't you go do this? Why don't you go do that? And she's smiling because she knows there's many times she asked me to do something and I have not been able to. But that doesn't mean that they're not amazing ideas and inspirations.
Can one of you give an example of maybe a time where modeling has pointed you in a direction that was completely non-intuitive?
I think so. One of the areas that Rich was talking about very kindly was we collaborated on these self-oscillating gels. And when they beat like a little heart. You put them in to a petri dish, and then you put chemicals in the petri dish, and they autonomously beat. You don't need anything other than the chemicals that you put into the petri dish. And we got very excited by these, and they had been studied, but there hadn't been any really good three-dimensional or even two-dimensional models for these systems. So that's when we made a lot of phone calls to Rich. Can you make this? Can you make this? And we were particularly interested if you could have finite pieces, if they beat like a little heart, how do they communicate? And if I put two of them into a soup of polymer, how do they talk to each other? Do they talk to each other? And we had some ideas, and Rich showed those ideas. He actually experimentally demonstrated how they talk to each other, that they do talk to each other, what are the limits of how far apart they have to be in order to communicate. So it was throughout, I think, our careers, we've had that very nice back and forth.
Yeah. And it's that's what makes it fun, right? I would never done that without the partnerships across with folks like Anna and Jesse. That's why I think we still enjoy doing what we've been doing for so long. And it leads in directions you've never thought of. I mean, we now ask questions of, what is the information content of a material? Is there a property of a material that reflects how it can process information? These are questions we don't have answers to, but we would never went that direction without the just ideas of, I have two blobs that beat autonomously. How do they talk to each other? I don't know, Jesse, you were going to say something?
I always consider modeling to be a critical part of our design loop process, where you really need to be able to create and sustain a model, be able to fabricate what you're trying to accomplish, and characterize what happened at the end of the day. And then you essentially repeat that process loop. And the power of modeling is incredible. We use it to explain the experiments that we tested out and what happened during the experiment, because all experiments don't go as planned. And then we also use it for predictive capability as well, and say, well, this happened during this experiment and we learned this and we collected these properties. But what happens if we change a variable? And we can use modeling to predict what will change once that happens. So I view it as core to what happens in our scientific design process. And it is very powerful in both understanding and predicting.
I just want to comment a little further on the lovely thing that Rich said. So we've both been very interested in the idea that materials inherently contain information. They inherently contain the information the process by which they were made. And so we wanted to extract that information to understand all the different forces that went into play to make this material, and then to design materials using those forces. So that I think is one of the great challenges, there's nanoscale information in the material. And we want to understand, if we could talk to it, we could say, how were you made? And then understand the basic physics of how they were made. And then using those principles, then design other materials.
I like that. See, it's almost like nanomaterials investigators. Like, you guys are learning about these materials, then trace this path of how it can be recreated. Like, that's really cool. And I kind of want to extrude that a little further and kind of go into, we've talked about graphene, we've talked about some real examples of what nanomaterials can look like, even with the great visual of using Scotch tape, which I had no idea. But let's talk about what's being done now. So I want to start with you, Jesse. Let's kind of cover what are some of the things that your teams at least do with nanomaterials to affect the everyday world. Let's say with one of our consumers or people listening to this now, what are you working on now that they'd be familiar with? And furthering that, maybe it's a success story or something that you guys have gotten out there that could be an example. So over to you to touch on that.
Yeah, absolutely. So, Ken, my role in what I call the nanotechnology life cycle in industry is to really bridge the gap between these interesting properties that we observe in the lab to well-characterized products that have reproducibility at a larger scale, which we can utilize. I work on qualifying these nanotechnology products for use in our applications. What I do is I put those into these nano tools or nano products into a toolbox. And then our clever systems designers reach into the toolbox to utilize these tools in a meaningful way. What's unique about the aerospace industry is that when we work on something nano related that goes into, for example, a plane or a satellite, again, it's something I can reach out and essentially touch at the end of the day and see its first flight or its first launch into space, which is extremely rewarding and inspiring for me to be able to push those boundaries. In terms of successes and impact and relatable transitions of nanotechnology. I'd like to give you an example of our recent James Webb Space Telescope. So on that program, we utilized very thin, nanometer thick, so to speak, coatings that were applied to the sun shield of the James Webb Space Telescope. That sun shield shields the cryocooler instrument that enables it to keep the infrared sensor from getting too hot. And when in so doing that, it enables the James Webb Space Telescope to take all these amazing images that you're able to see in the media and that are being released by NASA. So that's one example. I also took my family to the Science Center in Portland, and they had an exhibit dedicated to nanotechnology where it makes its way into our everyday products like cosmetics and tennis equipment to create an ideal ball bounce or a more stiff racket. Also, nano-sized features that we call corner cubes that are seen on stop signs at nighttime that return a bright light return from our car headlights at night. And even there were examples of quantum dots in displays in TVs, for example. And our cell phones are adopting flat optics that focus and correct the light onto these small cameras, so our phones can be smaller and smaller all the time. So these are just some examples of how nanomaterials impact both what I do in terms of military and civilian applications.
Trying to understand what the benefits versus the cost is also an incredibly interesting thing. But along those lines, Rich and I worked on polymer clay nanocomposites, which were a mixture of mud and polymers, and you wanted to get mud particles very dispersed. And so Rich did some extremely beautiful work, and then we was inspired by his work. And then everything was great. Everything was wonderful. We loved it. And then one day, I think I did consulting somewhere, and everything went okay until it was the price per pound. And then, the project was taken off the table. So there is both a health cost that has to be taken into account, and then just sort of life cycle, the total physical cost, where it becomes, is it reasonable to make car parts out of clay and polymers?
Yeah, Anna, those are all great comments. And I think it gets to, there's lots of potential in the scientific literature and excitement, and that is hard. But what's even harder is taking those ideas and then working it through all the illities: availability, manufacturability, sustainability, and putting it into a product that's manufacturable. And I think that's what Jesse was given some outstanding examples that just, epitomizes what I believe nanotechnology is, which is nano inside, to borrow somebody's great branding from many years ago. But it's what makes things work. You're never going to touch nano per se, but nano is used in a lot of products, not only in the final product, but in the route to get to the product. I think one of the challenges that we work on here at the Air Force Research Lab in partnership with Jesse and other folks in industry is connecting the potential to the application and working the illities along the way, whether it is the gold standard data sets that allow you to do the engineering models to say, yeah, this is going to be performance-wise more valuable or costly, so that your additional cost leads to better performance, and so the final investment is worth it. To scale up, can we make enough of the material to actually test it out and make it available? Just as another example of the excitement that was aluminosilicate nanocomposites, and I'll use a mineralogy term there, phyllosilicates, montmorillonite. You could add the layered silicates to the plastics, make amazing properties with very little filler. But at the end of the day, it was a new filler into the plastic recycling stream. And in some of the large scale applications like food packaging, automotive, It just did not make sense when you started running the numbers on circular economy, as Anna was talking about. And these were concerns that happened 15, 20 years ago that really limited some of the large scale infusion of those technologies into the commercial marketplace. So yeah, it's a complex path from innovation to application. In a lot of things along the way, work from folks like Jesse and at Northrop and others in large companies really are the reason why you can walk into Sam's or Costco and buy a quantum dot TV, and you have quantum dots there. That is as nano as you can get, because those colors are because of the size of the material.
Anna brought up a great point talking about the cost per pound. That's extremely important in the industry that I work in. Cost per pound is probably as much or worth as much as any other industry out there in aerospace. The cost per pound to launch satellites is enormous. It's been coming down over the years, but every pound that you can save either means that I save an actual cost, or I can put, if I save enough pounds, I can put additional capability onto my satellite that didn't exist before, or that I couldn't get through enough mass savings. And mass savings is really where nanomaterials first really saw their true applications in the aerospace industry. So that's an incredibly important point that Anna brought up.
I think this discussion, emphasizes that nano is not new. We can go back and look at ancient artwork clear up to today. So then that begs the question, why now? And I think it comes back to something we were talking about before, was the invention of the tools. The ability to see, measure, manipulate, and model. The things Anna were talking about, the models, they did not exist until she had to create them to do these types of calculations. And the engineering tools Jesse's talking about that incorporate nano didn't exist until we saw it. But all these tools is what enables us to look at the world around us, find things we hadn't seen before, understand them, and then go take our engineering mind and make it and do something with it. And so I'd say the future of nano and the future of this whole area continually relies on new tools, new ways to measure at the few atom level, new ways to see, new ways to calculate the effects across length scales. Quantum correlations is a great example of a cutting edge area in nano, which requires new simulation techniques, which require new measurement techniques. And my experience as these tools come online, that's the predecessor of where the next great, or the next, I shouldn't call it great, but the next exciting observation or invention will come from, that really drives the community in one direction or another.
I think that brings up a really beautiful philosophical question that I've been fascinated with. The science you do in any age is limited by the tools you have. So your interpretation of what is happening in a particular system is biased by or limited by, this is a tool I have, this is a length scale that I have. So I totally agree with Rich, and the development of new tools makes it very, very exciting. But you wonder, in previous times when people didn't have these tools, their notion of physics, their notion of science, their notion of what happens when you put these materials together was not as well informed, but still extremely interesting.
You're absolutely right. I mean, even look at things like the heliocentric model and other things. It's the idea of the thought process, but then the application of, do we have the right way of testing this, or at least talking about it? And I love that quote. The science you do is kind of limited by the tools you have. I might get them to sign behind me. But I do want to kind of further that too. So we're talking about the future and looking ahead. And we talked about some of the challenges here, like whether that's, scalability, affordability, recyclability, the ilities, as you said, Rich. So I kind of want to throw it out to the group. With these developments we're talking about, I assume that's what we're kind of tackling, but is there new, whether it's tools or ways we're kind of approaching it, that's kind of making that easier in those ility scales? Starting with you, Jesse, what are we doing to make those, I guess, more effective for cost or making it easier going forward?
Yeah, there's quite a few challenges out there. The field is just becoming increasingly complex, where you can't just have a small group with different backgrounds. You really need a diverse team to be able to really tackle these problems because they're becoming more and more difficult as our understanding of what happens at the nanoscale, how we can understand it and then, control it, manipulate it to the best of our ability. So when I'm building a team, I really look for a diverse set of backgrounds so we can come at it from different solutions and how best to move forward. We're really, I would say, going as small as we can possibly go. Right now, we're going into the nano realm. So we're trying to take those nano building blocks and create something larger that has unique multifunctional properties that come with it. For example, what we're trying to do nowadays is make composites where we're able to have unique and controllable or tailorable electrical thermal properties and also be highly radiation resistant. As we go to exploring new parts of our universe, that radiation levels change as a function of where you go and how far you can explore. And so we have to create these composites in a sort of designer fashion where the nano composite will significantly outperform a bulk material like what is traditionally used, such as aluminum, for example. And so we can get a lot of different capability out of the same area, so to speak, with nanotechnology. And so there's many challenges that we have, but those are some approaches to how we can try to overcome those and how we can be able to look at the problem differently, so to speak.
Dr. Tice was talking about needing this large, diverse team, and that was right after talking about needing a diversity of tools. And, Dr. Balazs, you put it exactly right. We can only do the science that our tools allow us to do. Does that mean that there are certain pockets where people don't have that access to great teams and great tools? And how do we go about solving that problem?
That brings up a very beautiful question. There's a group of people who do medicine for all. And so because there are locations that do not have vital tools for healthcare, for example. So they've created these portable devices so that you can use them in remote locations or where there isn't very much power. There isn't quite that yet for nanofabrication, but there hopefully might be. For nanofabrication and manufacturing, what I think is a really beautiful concept is the self-organization. So materials can assemble themselves, and self-organization is the dynamic process by which, so it involves dynamics as they self-assemble. So your question is wonderful because at the end of the day, you'd like that material to make itself. You'd like to know enough about that material so that when you put the material components in the jar, it self-organizes into that object which you wanted. And I think that's one of the next challenges, and hopefully then that will make it more available to everyone.
Does that mean that the Air Force is going to put all the parts of a plane in a very large jar, shake it apart, and we'll have our next jet?
Absolutely. I mean, that is an end game. That is an end goal. That is an end desire. You can do that on small scale. And it's exactly what you said, put the parts in and shake. How far can you take it? And I loved your example.
We had leadership at one point who had commented that wouldn't it be great if I could write the DNA to grow the satellite? And so, yeah, I mean, I do agree with you, Anna. Those are a vision of how to assemble, how to get things together. I just bring up an example of John Main. He was a program manager at DARPA maybe about a decade ago. He had a program called Atoms to Product, A2P. And I think it was a fascinating concept in his program. He asked the fundamental question, how do you build something when you have the tools to design at the atom level, but your product is a 747? So you're bridging 10, 12 orders of magnitude. You can't do it atom by atom at a time. So how do you structure that? How do you do the workflows? How do you think about doing that, do you have a finite alphabet at each level? And if you do, how big of an alphabet can give you the maximum amount of design flexibility? And then where do you break it off to use different manufacturing approaches? For example, the self-assembly, directed assembly, kind of what Anna was talking about, the small scale, but then moving towards lithographic, robots, et cetera, at higher and higher scales. I think that thought process is still an unknown. Nature and just human manufacturing, I think one of the things that came out of John's program was it's roughly 3 orders of magnitude. You build something with components that are 3 orders of magnitude smaller than your product. And if you want something bigger, then you have those parts that you put together. And it's starting to get it at the systems engineering, pushing it down to the atom level. And I think that's one of the big frontiers in nanotechnology, in materials, that isn't really chemist driven. It's not physics driven, but truly engineering driven. How do you do the systems engineering and put those bounds on what is the right alphabet rather than infinite letters? What is the right processes at different scales, and how do you piece them together to make products, which, Jesse's world at Northrop Grumman and others in the commercial world, whether it is, SpaceX or Tesla or Ford or other industries are really striving to do. I was going to add one additional thing, which I think ties the nano world together with the broader material world. And it's really the adoption of I would call it the tools of the digital revolution. This convergence of big data, analytics, of high performance computing and models, of automation, and ultimately AI tools, machine learning, decision-making tools. When you close that entire loop, you can automate. Not only automate, but you can make research autonomous. You can ask the system to do something, and it can learn on its own and tell you how to do it. A great example that's been in the literature that's very nano related was the Aries system developed by Benji Murayama, where he and his team showed that you can autonomously grow carbon nanotubes at a rate. He developed a robot that learned how to grow carbon nanotubes at a specified, at whatever the human wanted the rate to be. And there's hundreds of variables in growth of carbon nanotubes, and being able to pull all these tools together and demonstrate that, I think is core to the acceleration, not just discovery, but to the development and deployment in the manufacturing across the board. So I think the fundamental way that Jesse, Anna, myself did nano is going to fundamentally change. It's going to be a big data problem, and using the tools of the digital revolution will allow things to move much, much faster to solve stuff.
I agree with Rich. There's huge opportunity space in discovery of nanomaterials. We've been witnessing, the big data digital revolution, but I think that's really manifesting itself through a few initiatives. One was referred to as the Materials Genome Initiative, which helped the discovery of new materials, which really spurred on high throughput experimentation, where we can do massive amounts of parallelized experiments and characterization and discovery that happens quickly. And once we determine a material that has those interesting properties or composite set of materials or alloys, that's when we really need to take those and scale them up to the large quantities very quickly. I'm going to borrow a term that I heard from Rich that I'm not sure if he coined or not, but I'm going to give him the credit for it. Was we have to be smart harvesters and rapid integrators. We really have to understand where the breakthroughs are and then rapidly integrate those into our products that give us quite a bit of new capabilities. So that's really where I see a huge opportunity space moving forward. It is really through the rapid discovery and then rapid scale up to be able to put those tools in the toolbox that we can leverage in the future.
You did mention that. I thought you were going to say that what Rich mentioned earlier, that we can like tickle the materials right to make sure that they actually do the characterization. And I was like, that's a great term. I like both. But
Yeah, thanks, Jesse. I don't remember saying that, though. I used to use the term harvest a lot.
But you guys have brought up a great point of talking about these diverse teams, areas that need to be like focused on in the discovery that's important, really the evolution of nanomaterials. So I'm curious, so many of our listeners probably are too, how are people able to join this field? Is there a specific like major they should be going after? Is it accessible to anybody? So kind of your guys' experience, somebody saying, hey, I want to work with nanomaterials like Rich, do I have to get a degree in that? So what would that look like to join, let's say starting with you, Rich, somebody in AFRL, if they want to work on similar things?
I would start by saying there is no one discipline to go do nano. As we were talking about, it requires chemists, physicists, all types of engineers, computer scientists, data scientists. And if you're moving towards business and you're moving towards deployment, you need people with business skills and understanding the marketplace also. So to be involved in the nano revolution, nano products, there's not one particular degree, I would say. The thing I would recommend, though, is that in any degree you choose, emphasize understanding what other degrees do. It's about that interaction. It's not just being the material scientist or the materials engineer, and that's all you do. It's about understanding how all the pieces of the puzzle fit together with the different disciplines. But relative to, can I stop at a bachelor's? Do I have to get a PhD? No, I think the world is, and the community is large enough that there are needs of all levels of education. And especially when you start talking about taking the innovations and developing products, developing the manufacturing, and then deploying the products to parts of the world that may not necessarily have the science infrastructure that the United States has. Huge opportunities in areas such as energy, water purification, and those innovations that have developed over the last 10 years, getting them into products and getting them into the hands across the world. We'll take all types, all degrees to do it.
I would also add that if you're listening to this podcast and you're an educator or you're thinking about secondary education, I would refer to nano.gov. There's a lot of excellent resources on there that help you explore the world of nano, and you can do it at your own pace, at your own level, and just get yourself familiarized with it. That website has a lot of great information for both students and educators out there. I would also like to echo, I guess, Rich's comment is that, yeah, we really need people of all different types of education levels and background to contribute in the space. And there's a need for everybody to play a role in terms of maturing and innovating a lot of the great technologies and materials and contributing to discovery and science and how we blaze a path forward in terms of the future of nanotech.
So Dr. Vaia, you talked about things like energy and environment and water, and there's so many, obviously all of you are thinking aerospace and these types of things. There's so many different industries that I think nanotechnology can touch on, make an impact on. But I wanted to go back to something that Dr. Balazs mentioned, and that is, how do we responsibly develop these materials? How do we explore scientifically what is possible, at the same time really being thoughtful about asking the right questions at the front end? Are we doing that? How's the community go about responsibly developing these materials that have high potential to do great good, but we also want to get in front of some of the potential unintended consequences of entering new, stronger, faster, better materials into this world?
I think there's an incredible interest. I mean, that's a brilliant question, and that there have been a very large numbers of communities who are now recognizing that, who are specifically saying that over and over and over again, that there has to be responsible design. You can't put drugs into your body that will eventually give you cancer. And so that that process, I think people are starting to look at very, very carefully. And that's a really nice trend that has just evolved from the community.
And we're talking about evolutions of the community, talking about like ethical approaches here. And Branden, you included as the co-host. I'm curious because we kind of started talking about this a bit. So where's this all being talked about? I know we have this here to bring all these brilliant minds, but are there like different conventions happening? Like, is there a group of nanomaterials or like researchers? Do you guys go to an island somewhere and just hash this all out? I guess, how is this happening between industry, academia, and AFRL? Like, open question to the group, but where are people talking about this so we can make the right decisions?
Well, there are a huge number of conferences every year. There's the Materials Research Society meeting, which I think Rich was very involved in. And that's the place where people gather to brainstorm and hash these things out. So the national conferences give a great platform, a great place to do all of just that.
I would add that the American Chemical Society is another great conference where a lot of the ethical implications are discussed and openly. And there's panels and sessions dedicated to the impact of science and technology, and especially nanotechnology, on what we're doing in terms of environmental and other types of impacts to society in general. So that's a good forum to explore as well.
I think, Branden, I'll also add that I've seen over the last decade or so an infusion of ethics in the engineering curriculum. And I think that's an important, very important change in addition, in the sense of, we're talking about nano and the challenges nano can provide to the environment, human health, et cetera. But it's one example of any new technology. Every new technology has an unknown. That's why it's a new technology. And how do you put the guide rails up as you develop the unknown and assess the potentials? At the end of the day, that has to be embedded in the way innovators think about exploring the new as well as implementing the new technologies. And so the more that is encouraged as a just as important part of curriculum as calculus, I think it'll serve all innovation well into the future.
But it's good to hear you guys all talk about the integration of some of these ethical concerns, and this is something that here we are on the AFRL podcast and thinking about what the federal government can do. The AFRL is a very active member of the National Nanotechnology Initiative, which at its core is meant to bring all the various aspects of the federal government together to think about the development of nanotechnology, nanomaterials, and that includes, of course, the research and development arms of our federal government, folks like you at AFRL, but also integrating them with other experts, including folks at the National Institutes of Health, for example, or the EPA, the Environmental Protection Agency, so that they are all working together and applying their own expertise from the basic science to the applied, to the regulatory and the health, and putting it all together. And we talk a lot about this in this podcast, about collaboration and different expertise. That's what's happening at the federal level. And so it's really good to hear your perspectives, in the laboratories, that you're also thinking about these things, also talking to the social scientists and making sure that they're helping us ask the right questions as well as answer them.
An outcome also climate change, and we started to become very aware of the things that we are doing are detrimental to our surroundings. And so as that became more and more apparent, we started to ask that question in more and more arenas.
So talking about climate change, I'll throw this one out at you. What's your favorite nanotechnology solution that will help to address climate change? Because there are a lot of them.
I gave some examples earlier of why I really got interested in the first place of nanotechnology. And what really spurred me on was the ability to harvest energy through solar cells. And the materials that I was making were molecular precursors that would enable thin film deposition of new materials that could absorb different parts of the sunlight spectrum that we just didn't have access to at the time. And absorbing more of the sun's energy and be able to turn that passive source into a clean energy source really is, in my opinion, what really got me excited about nanotechnology in the first place. And that's what really got me into the field. And I still get to apply those same principles today. And I really am able to touch on a lot more different types of topics as well. So in general, that's really how I got interested in the topic in the first place, is just being able to make newer types of clean energy, which ultimately will impact, climate control and climate change.
Yeah, Jesse, if I could build on that, those innovative technologies for energy harvesting, energy storage also are saving and hopefully will save soldier lives in the future. The ability to create energy from your environment, harvest energy from your environment, means that our logistics trails to supply the fuel, supply the water to soldiers in the field or airmen on remote bases will be much less. They'll be able to operate the base, operate their forward location with all the technologies we're developing to address climate change, but will also allow them to operate and reduce the soldiers and airmen and sailors that are necessary to bring the convoys of stuff that they need. And so I think the back and forth between the technologies to address climate change also have a large impact on our ability to protect our men and women when they're out in the field and defending the nation.
No, agreed. But that's a range of applications, like we said, all the way from civilian to the military side, from the climate to getting folks home. So I kind of want to, speaking of bringing it back home, let's kind of like get a nice bow tied on here and open things back up to the forum here for the group. I'm starting with Anna. Any final thoughts, things you'd like to share with the folks here? Any takeaways they should know or things we may have missed? Jesse, over to you.
Yeah, I just want to say that this is a really exciting field to be a part of. I'm glad that I'm a part of it, and I'm really interested to see where things head in the future. It's a really interesting time as we learn more and more about nanotechnology, how to be able to control the properties that we're looking after, being able to discover at a faster rate, being able to have the tools to scale up and observe at a faster rate in the future is really going to have a tremendous impact, I think, on we as a country, we as the world, and where we move in the future. So I just, a parting thought for me is that I'm excited to be a part of this, and it is a really exciting time.
And Rich, over to you.
Yeah, I guess I'll put on my chief geek for materials for the Air Force and the Space Force hat on here. Everything is made of something, and that is actually the vision of our organization, as we're inventing the stuff that makes the future. And I like to think that way back to when the Wrights flew, Charlie Taylor, innovative casting of his aluminum block engine that allowed the Wrights to fly, because he beat the requirements and he delivered an engine that was beyond what the Wrights needed to take first flight. But that included nanotechnology. That innovation included Guignard Preston zones because of the copper and how he processed it that effectively precipitate and hardened that aluminum. To the things we're doing today, the aircraft, the spacecraft, they're incorporating new materials, and it's about that structure. How do you make the structure give you the performance at the weight and the cost that's necessary? And that's what Jesse was talking about with, the James Webb and other satellite probes that are out there are all great examples of that. I guess what I'd like to close with is, the Wrights took flight not knowing what they had, but they did because of Nano. We're flying today with selective choices of Nano. I just hope the future is just as different as the Wrights were to James Webb because of what we're able to be working on now and getting it into the commercial commercial marketplace. Who knows? Maybe some things we see in Star Trek and Star Wars will come to fruition. I guess that's what our hope is, and what drives us to continue to do this day in and day out.
I'd like to make one more comment that not all these advances need huge pieces of instrumentation. What it really needs is innovation and new ways of thinking. For example, soldiers are wearing glasses in places where the sand is thrown into their eyes and thrown into glasses, and then that scratches them and doesn't make them very effective for the next use. And if there are nanoparticles in there, then in the evening, you could put the glasses in at a certain temperature of hot water, and the particles will diffuse to the cracks and fix the cracks. So that's innovation that didn't need huge instrumentation. So for kids in the future and people going into nanotechnology in the future, that's an exciting way to think about it too. And that's where people can contribute as well.
Thank you for that. I mean, I was going to say, at the end of the day, you're turning science fiction to science fact in many ways. Like, this is the conversations we had from some of the cooler terms, talk about quantum presses. I mean, even going back from like archaeology and the ancients till today, we've covered the gamut of history. And honestly, I'm looking forward to what's next. So I just want to thank you all again for taking the time to talk to us. I'm sure this won't be the last time, but thank you again for sharing your expertise and thoughts on nanomaterials.
Thank you.
Thank you.
Thanks, Ken. Appreciate it.
Make sure to follow us on social media at Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And remember, stay curious.
Logging off.